So today is the last day of the course, and we go and show you other representations about features of C++11, and also something more advanced is like how to use this to actually implement certain recurring structures. So we go today doing we cover lambdas and functions, and the context per keyword. We have the traits, patterns, and then we have a part about the STD threads and futures and multi-threading in C++. And we have also a part on STL. We also wanted to have some space for exercises like we did yesterday. So we don't know if we cover the whole thing. So we will try to do our best to cover at least the things that we think are most important, and then give you some time for the exercises. If you go on a web page, it's written the C++ course is a 2.5-day event. We probably had some miscommunication there at some point. This is basically a 3-day event. So, but we give you all the slides and everything. So if you have to leave early, you cannot stay until the end. I don't think it's going to be a big issue. How many of you are going to attend the HPX course? Oh, okay, good. Yeah, you will need to. If you know already something about the STD threads, that would help, and also async, and so it's going to be good. We have to cover that. Okay, well, let's start with lambdas and functions then. So C++11 introduced the concept of lambda. Lambda is a very old concept. It's been born in 1930, 35, and 36. And it comes from the concept of lambda calculus, in which the only thing you're allowed to do is to call functions and get functions that calls other functions, and etc. And it's the base for the functional programming. So most of the functional programming is based on the lambda calculus. And C++ didn't have something to natively support a lambda concept. So in C++ before 11, you had to declare any function with a name or as a class of some kind to do a functor or a function. And you can now use lambdas. And lambdas are unnamed functions. They are functions that do not have a name, but you can call anyway. You can pass them around. As many other features of C++11, they really changed the game. They really changed things, how you think about coding, like STD forward. We show you the STD forward that forward the argument as maintaining the referenceness of the arguments. That thing might seem like something you would never use, but when you start coding, you will find out that at some point that thing pops up and will simplify your life in so many ways. Another thing is auto. Auto, you might think is simply because I don't want to think about the type, but it actually helps in getting you better code, and without that code complexity that otherwise you would have to implement. So lambda is also one of these things that really at the first time maybe you say, why I need a named function, and then after all you say, wow, you use it everywhere. Except when you cannot, and then you say, wow, I really wish I could use lambda here. So there is a special syntax, which is the underlined line over there, which have a square bracket an open and close square bracket that indicate, okay, I'm declaring a lambda here. Parenthesized list of function arguments. And in this case, it's an int a and int b, right? It's a lambda that takes two integers, and they will be called a and b inside the lambda body. Then you use the curly braces to put the code that you want to execute. And in this case, you will have a return statement that returns a plus b. You can then take this guy, you can take this lambda, and you can assign it to some function, to some variable name, and you basically have to use auto because you don't really know what the type of that guy is, even though it has a type. Okay, it has a type, but the type is decided by the compiler. Also, so the compiler decides what type give to that guy. It will give a name, some internal name. Then you use that type simply using auto. So you're not supposed to know the type. And going back to Maxime's question, is this going to be Python-like or not? Yeah, okay, maybe. So then you can take f. This lambda, you can call it as a function. You can pass it to other functions. You can pass this lambda to other functions. It's just an object in some sense. And so, for instance, you can have a for each statement here on a vector that instead of passing a functor of some kind, you pass just the lambda, and the lambda will take a reference to the element type of the vector and by reference, and then it will increment the values inside the vector. In C++ pre-11, you have to write that functor outside somewhere. It has to be in the scope. It can be a functor, it can be a standalone function or something, but it has to be declared somewhere else. Now you can see all the code that you have to write is in there. It increases code readability substantially, as long as lambda is not too big. That in case it is too big, sometimes it might be too intrusive, but it really helps to write better code so you can control what's happening. You see what's happening. What is the mental model to think about a lambda? Well, a lambda, in practice, can be seen as a class or a struct, as you want. So the compiler will see that syntax and will generate internally something like a struct with some name that will put there some name. Usually, after the name is something like the name of the function where you are in underscore lambda 0 underscore lambda 1 or something like this. So there's really a very simple naming scheme, but each compiler uses a different name scheme, so you cannot rely on that. So you create a class with some name in which you have an operator, parenthesis, which takes the same number, that takes the same parameters of the lambda. The operator is const, so the lambda is not, that does not have a state. Basically, the idea is that you don't want the lambda to have state. And then inside the body of this operator, simply have the body of the lambda. So this is the mental model. How can this work? Well, just create a function object, and you pass the function object around. This is just a mental model. And this mental model works also to try to remember then all the other rules that imply lambda. This is the most simple lambda you can have. Actually, the most simple lambda is the one without any argument. The most simple lambda is open and close square bracket, open and close round bracket, open and close curly braces, which is a quite funny syntax for lambda that takes no argument and does nothing. The lambda allows you to capture variables that are in your scope. For instance, in this case, I have a variable, a type integer, t, and inside the square bracket, I put t, and I'm communicating to my lambda, capture this value and make it available inside my function body. So in this case, I have a lambda that instead of doing a plus b, just multiplies also the thing by t, and t is the variable that is defined in my local scope. And I can take this function and pass it around in other scopes. It will survive even after t has been, it went out of scope. How this works? Well, the mental model kicks in again. If you want to understand why this is actually possible, what is the kind of, what you can do with this, it's like you having a function object that has a data member which is initialized to the value of the variable at the beginning, well, when the capture happens. So you construct the lambda with that value in, with t. You store the value inside your lambda as a data member, and then you use the data member here. As you can see, this is const. The function call operator is const. It means that t cannot be modified. So if you modify the t inside the lambda body, it will give you a compiler error because t is not modifiable, right? The function is const, and you cannot change it. And this is a copy. So there is a copy that happens from this t and the data member here. And it happens to have the same name, but it's not the same object, two different objects. Please.
So if you modify t outside the lambda, t inside the lambda stays a, right?
Exactly, yeah, okay. If you modify t, yeah, it's okay. I will repeat the question. The idea is that if I modify t after I declare the lambda, so after that sentence I put t equal 9, and then I call the lambda, yeah, t is still equal 8. The value is captured at the moment of the assignment, when you define your lambda. In this case. If you can wait for a microphone.
When you capture t by reference, is it still const, the operator? Because you can modify it then, right?
Yes, but you can modify the value referenced to the thing, yeah. But it works, yes.
But then the operator is not const anymore.
No, it is const. It is, you can try it out. It is const. It's like having a pointer. You're not changing the pointer. You're changing the value pointed to. So it actually works. So it is still const. Yeah, we'll get to it. We'll get to it later. Yeah.
The value of t is captured before, at the time of declaration of the lambda, or at the time of the calling?
The time of declaration. Think about that line, something that transforms into a function object that is instantiated when I assign to f. So whatever is the value of t at that point is the value that is captured. When I call just the function call operator. Another question?
I understand how it works, but I don't understand why you would do that. Because it seems dangerous to define something, but then later on you use it, but you forgot what the t argument was set for.
In this case, it's quite safe, actually. And you know when you declare the lambda what t is, And then you use it later on, and you never look at the code again, right? You have the f, and you pass it around. So you prepare your function with the values that you have at the moment. So it's not that dangerous. It becomes dangerous when you have references. And we'll go into that later. That is more complicated. But the fact is that t is not the same t as it is outside. It just happens to have the same name. And this might actually be a little confusing. I don't know if it answers the question. We will see, I guess we have examples in which show you how why. Well, why this is useful is because it will pop up everywhere. It will be quite easy actually to use it using these captured by value. This is capturing by value something. It's really like constructing a class with a certain value. So it's not, it's quite safe and quite intuitive in this particular case. No, it's not like Python.
What does the compiler do exactly? You really replace the code by the strict code?
Well, you don't know. The error messages that you get are like you have released something like that, especially in the GNU compiler. The standard doesn't specify how this thing is implemented, but this is actually a good model of what is really happening behind the scene. So we said before, t is constant, cannot be changed by the function operator. So my body of my lambda can only read that value, cannot change it. And so, oh, that's inconvenient. So I won't be able to do it. And to do so, you can put the keyword mutable, and it will do the trick. Who's familiar with with that keyword in C++? Who already saw that? Okay, you've never seen this keyword. No one knows. So, okay, mutable is something that existed in the pre-C++ 11. It's like you have a class data member, and you stick a mutable keyword in there, and that means even if the member function I'm calling is const, I can change the value of that data member. Okay, mutable say, okay, forget it. If it's a const, change it anyway. So you stick the mutable keyword, which is reused for this lambda. You put it here, which means all the captures becomes mutable data members. So inside my function, I can increment t and then multiply for it. Again, this is not the reference. T is not the reference to my initial variable that I captured. It's a data member which is initialized to that value. That is incremented every time I call the lambda. It becomes a stateful lambda in some sense. So this data member will be incremented every time I call the function. The value of t outside will not change, because the value of t outside is being copied before doing it. So you have a constructor that initializes t to the value of 8, and then the function operator is still const, and you increment t anyway, because it is allowed to do it, because it sticks the mutable keyword in front of it. So this gives you ability of building stateful lambdas. So you've seen you can capture variables by value by copying it. You can modify those values inside the body of the lambda if you stick the mutable keyword. Something that is available only in C++ 14 is the ability of writing generic lambdas, in which the types of the arguments are not known when the lambda is defined. So I define the lambda that takes something, O to A, O to B. No, it's not like Python. And, and this becomes, the mental model of this becomes the same as before, only that. So I have a little of sore throat. I hope my voice doesn't sound much like Obama. But so this becomes a templated function call operator. Okay, so this becomes a function object as before, only that the operator is templated. And this mental model holds everywhere. So it really works exactly as a template member function. So when you call the function call operator, the template substitution thing happens. If a version does not exist anymore and does not exist yet because it's not been called before, that member function is created on the fly. Is created by the compiler and called then when it is needed. And this is also a very useful feature. It allows you to really use the lambdas in an easier way. So it simplifies your code. It removes the thing that you don't have to. In the initial example with the for each, you have to know, okay, it is an int reference that is happening there. You can put auto reference there, and then you get the actual type, so you don't need to know what the type is. And this helps when you have to, when these lambdas are called inside other functions. This is something I didn't mention, but conceptually, generic programming, as was mentioned yesterday, relies a lot on high-order functions. So functions that takes functions as arguments. This is very common in functional programming. Actually, this is the way functional programming works. You pass function to other functions, and this creates other high-order functions, which is slightly different than the callback strategy. In the callback strategy, you pass a function to some other function, but that function is still in your own flow of execution, right? I said, okay, this is a callback. When something happened, call this function that I'm going to give you. High-order functions, you really give the function to the other guy. Say, I give you this function, now it's yours, it's not mine. And this is why, in this case, you pass a generic operator, and then will be who gets that lambda that will instantiate the proper operations, will actually instantiate the member function that it needs. So it really enables high-order functions. In C++ 14, oh, yeah, question? Well, this is actually wrong code. Sorry about that. This is a buggy code. Why do I need X? For no reason. Just didn't pay attention when I was writing the slides. I just capturing X. It's right. I mean, the first two lines are right. They works. Only that X is never used inside the lambda. And the other one is auto X equal, which will work in Python, but it will not work here because X is an integer. It cannot be assigned to anything else. So that is wrong code. Sorry about that. All right. C++ 14 offers also the ability to rename variables inside the lambda. So I can say I want to capture the Boolean, but I don't want to be confused by the fact that the name is the same. Right? I want to give my own name inside lambda, and I can say the flag equals sum, and then inside my lambda I can use the name flag, which has the value of sum when the lambda was declared. Mental model is that I have a data member flag, and I simply initialize flag with the value of sum. So I construct x with that value. And then the body remains exactly the same. The body is exactly the same. So back to C++11, the capture can not only capture a single variable, it can capture a number of variables, and can capture variables different ways. So in this case, you have a capture sum, which is a Boolean, and I capture x, but I want to capture x by reference. So I put an ampersand in front of x, and I'm saying to the lambda capture this x by reference, or whatever I change x inside my lambda, the value of x out in my scope also changes. And this is exactly as the mental, so the mental model works like this. You have two data members. One is sum, the other one is the reference called x. I initialize it as I would do in a regular functor. And then the body is exactly the same. I didn't want to put too much text here. It's exactly the code which is up there. And when you run the lambda, after you run the lambda, x will be modified accordingly to the lambda thing. And this can give you the problem that if you pass the lambda and you go out of scope, x doesn't exist anymore, and the lambda is a dangling reference. So you have basically a runtime error. So this has to be used with a little care. You need to know what, you need to reason about lifetime when you use this kind of constructs. Now, this is still const, it still works, because you're not changing the reference, you're changing the value which is referenced. So it actually works. Now, it might be tedious to capture all the variables. So instead, you can capture everything. And you can capture everything by reference, like in this case. In this case, you don't need the keyword mutable. You capture a reference. This thing can be changed inside your code. So you can say sum equal x equals 7 and do whatever you want. You don't need the keyword mutable to change it. And you capture all the variables which are in your scope by reference. And conceptually, what happens is that the compiler takes all the variables in your scope and creates this huge structure with all the data members corresponding to the variables. And I guess the compiler is not doing that really, but just checking what the lambda is doing. So the mental model here fades a little bit, but conceptually it really is the same. You can also capture everything by value by sticking in the square bracket the equal sign. And that means capture all my variables by value. They will be available inside. And to be able to change them, you need to stick the mutable keyword. So this is the same body, the same lambda body, but capturing in different ways. So one needs a mutable keyword, the other one doesn't need the mutable keyword. And you can also capture everything by value, except I want to capture x by reference. So there's kind of shortcuts to just do to just capture what you want in a quick way. So what is the return value of this lambda? In this case, it's fairly easy. The compiler deduces that the return type is whatever, in this case is an integer. But if it has to be something else, then you have to say it explicitly. And in C++11, that was happening basically quite often, and you have to specify with it after the argument list, you use the arrow and the return type that you want to use. So in C++11, this was actually mandatory in many cases because the C++11 standard doesn't require the compiler to be that smart, right? And C++14 actually requires the compiler to be smarter and to deduce the return type more aggressively. So in C++14, you almost never need to use this arrow. In C++11, you need. But there are still cases in which you want to use the arrow. There are not many cases, and probably not cases that you really want to do. But for instance, I want to have a lambda that does an in-place sum. So I want to see, I want a number a equal a plus b, and I want to modify a. And I want also to get back the reference to the guy. So this second example here takes a complex number, c by reference. This is the argument, it's not capture, right? And takes a complex d by value, add d to c, and return c. But what I return, I don't want to be just a complex number. I want it to be the reference to the original, to the first argument. And the way of doing it is to force a reference in the return type of the lambda. In this case, I could write complex reference. So I know that the return type will be a reference to C. And it's okay because it's not a reference to a local variable, it's a reference to something that comes outside, so it makes sense, at least from a language point of view. And you can also use auto if your type is complicated. Right? You can say, okay, auto reference, it takes whatever type that expression is, it takes the type of this expression, the return expression, in this case is C, and sticks a reference in front of it. You can do it by using this arrow syntax. One of the nice features of lambdas is that they are convertible. Convertible, is it convertible the right word? Yeah, it's not a car. It's not. Yeah. The lambda is convertible to a function pointer with the corresponding signature. So if I have a function run that requires a function pointer to a function that returns an integer and takes two integers, and I can pass there a lambda that takes two integers and return an integer. And this will be automatically converted to that guy, so I can actually do the call. And I can check that the pointer is not null. So the function pointer actually exists, and I can just call my function inside there. And as you can see, you can save code in this case. You don't have to write a function, give it a name, think what name should this function have. Oh, well, it should be called helper function number 1 or something. No, you just pass it and it will work. How about efficiency of the lambdas? Well, they are efficient as the mental model suggests, that you pass in the function object there and the compiler can do all the inlining it wants. So they are actually quite efficient usually. They are as efficient as any other solution you may come up with. There are some tricky situations, and you can find them in, for instance, especially when you port old code to new styles. I'd like to mention here the Cocos library that allows you to write algorithms and parallel algorithms, and is used to port old applications to new formats. And you put everything inside the big class, and then you substitute the your function with lambda calls, you return these lambdas, you execute later on using multi-threading strategies. There you need to capture inside the class. You need to put the lambda inside the class. So I have a class, A, that's a data member, A, and I declared my function operator, in this case, a function call operator of my class, which calls a lambda. This is a silly example just to show you what happens. The lambda captures everything by value, and it declares an integer, A equals 0, increments that integer, and then prints that integer. What happens if I call that function call operator multiple times? What would you expect in this case? So I call it once. What should it print it? This is 1. I call it again. It will print 1 again because there is a variable there. But now I want an alternate version in which I don't declare that integer, that variable inside my lambda. The capture by value will capture the data, it will not capture A. It will not capture the data member. It will capture this pointer by value. So it takes the pointer of the object, capture it, and push it in there. And here the mental model doesn't work because this code works. And this A is actually this arrow A. So this is the data member of the class. Okay, so this works. This is the data member A of the class. So whatever that value is, that is what is called. Yep.
Why does it work without the mutable keyword?
Because it's a pointer. I'm not changing this pointer, I'm changing the value pointed to. Good question. Yeah. It's not the same, right? The mental model captured these pointer by value, which means whenever I access these, start these dot something, I'm not changing this, I'm changing what this is pointing to, so that is allowed. And so you don't need the mutable keyword. In this case, this is implicitly done. So that A is actually substituted with this pointer to this object dot A plus plus. So consider instead of executing the lambda, they're returning the lambda to something else, to the caller, and then destroy the object and call the lambda. The object is not there anymore. This pointer is crap, and you get undefined behavior. So you need to be careful when you capture inside a member function. So this alternate function is actually the same as this one. Okay? It's like you're doing this arrow A plus plus, this A. And this is a pointer of the current object that is invoking this lambda, that is instantiating this lambda. Let's see another version which also works. You have a member function which declare a local variable A, then capture everything by value. A, in this case, will refer to the local variable in the innermost scope. And if I want to refer to the data member of my object, then I will have to use these arrow A. So these is available inside the lambda. So you can take this lambda, take it out, pass it to someone else, and they will be able to use it. And this will be the pointer of the object originally, where this lambda function was originally created in. Now, if I do like this, now this works as expected, because this will change the data member. Sorry, if I do like this, then I create a local variable, I create my lambda, I assign a to 3, and then I run my lambda. This second a will be 3 because it's the local scope. I change the local variable, and this dot a will be the value that this has at the moment of invocation of the lambda. This is different, right? Before I'm copying the pointer, not the data member values. So it behaves like a reference. Important difference here. This guy here, in fact, you can see that you don't need to put the mutable keyword here, because this behaves like a reference to the data member, because it's accessed through a pointer, like a reference, by the way. So in the first case, we see that there is the local variable is shadowing the data member, so it's perfectly safe. In the second case, this A is the data member of A, and the data member of A of the object in which this function is being called. And the trick is that this is captured by value. The pointer, this is captured by value. And this gives all the problem with lifetime. So if the object dies before I call my lambda, that is undefined behavior. I don't know what happens. This also shadows the data member, and so inside the lambda, you need to use a special care if you want to access the data member. In C++ 17, there is an accepted proposal. This will be C++ 17, in which inside the operation, inside the member function, you can capture these by value. You can take the object in which I am in, and I copy this by value, which means that inside this function, a++ will refer to the data member of a copy of the original object. Okay, and this is the safe way of getting accessing my data members, but also not having to be concerned by lifetime considerations. So if the original object dies, the lambda still have a copy of it. So it's still valid and still works as we expected. And this is just the syntax you have to use, you will have to use in the future, because now there's no way you cannot do it. Now you have to play tricks, and then it becomes a little complicated. So with the next standard, you can really do this and have a copy of the whole object instead of just the pointer. And of course, being a copy, you need the class to be copy constructible. Otherwise, you will get the compiler error that the class cannot be copied into the lambda. Any questions so far? I know that this thing may seem, okay, I would never need something like this. I would never bump into this kind of problem. When you start using lambdas, they are everywhere. So it becomes an issue at some point. I'm pretty sure at some point someone will run into this kind of issue. Okay, let's go into some other thing that related to this kind of argument, which is the std function and std bind. An std function is up here. It's a standard library facility. It's in the functional namespace, functional header file. So you include functional, you get function. And so now you declare a function, as a standard function that returns a float and takes 2 integers as argument. And you specify this as a template argument, so with the angle bracket. And I say f equal a lambda that returns returns a float given the two integers. And these will behave as a function, f3, 4. You can call it, it will just run that function. What you can do, so this might seem like, well, I already have a lambda, why should I do STD function? Well, STD function is more flexible, so I can take the same object, the same f, and rebind it, retargeting it to another function, for instance, to a standalone function, foo, that has the same signature, takes two integers and get a float, and I can say f equal foo, and that will, and I call still f in 3 and 4, and this will call the foo implementation. Then I assign f to an object, and this also will go and call 3, 4. This is called, you just run the function, this retarget the function to a standalone, and this retarget to the member function operator parentheses. This comes at the cost, so this is very, very flexible and super cool. If you have to use this kind of stuff, it really, really helps. It comes at the cost of a virtual function call every time you call the function f. So it is very flexible, but it's not that efficient. So you have to choose between efficiency and flexibility. Like all the time, actually. You have to choose between these two. So every invocation is a virtual function call. But given the flexibility you get, sometimes it's worth it. It depends where you put it. Okay, yeah, I mentioned later on about the conversion to function pointer. Another interesting idea in C++11 was to use bind. Now, who is familiar with the previous version of C++ might know bind first and bind second. Whoever heard about bind first and bind second? Okay. Yeah, so they are utilities that basically says I want to bind the second argument of this function to 7. So I have a function with two arguments, and I say now I want to create a kind of new function which is that, but the second argument of the function is always 7. Bind first will bind the first argument. Now, bind first and bind second has been deprecated, also because they were not so efficient. And instead, there is std bind. And to use std bind efficiently, you need a concept of placeholder. A placeholder is a class that has nothing but a name, okay, or very little less. It's just a name. As you know, if I declare a class A and I declare a class B with the exact same content, they will be two different types, right? A and B will not be converted to each other. The compiler is not going to see, oh, but they're exactly the same code, so they are the same type. Now, there are two different types, completely different types. And this is a good feature because it allows you to define classes that have that have different behaviors just because they have a different name. And placeholders are like this. There are classes and objects that are just names. So if you use the namespace placeholders instead of writing std placeholders all the time, you use the namespace std placeholders, and you have access to _1, _2, _3, I think usually until _9. But is implementation defined how many placeholders you have in your system? And the placeholder refer to the, basically in this case you use it to refer to an argument, to the index of an argument. For instance, here you say, I have a function foo, it returns an integer and takes two integers, our usual a plus b. And I'm saying I want to bind I want the function x that is foo, but the first argument should be always 4. Wrong. You see, when you try to fix things, it doesn't work. Okay. Yeah. Okay. This is why we didn't want to give you the slides before. So I want to create a function x that takes foo, and I want the second argument to be always 4, and the first argument to be whatever the user wants to pass. So now x7 becomes actually foo of 7, 4. Okay, is it clear? Number 1, refer the first argument when I call x, the first argument will be captured in some sense and passed to f as, in this case, as first argument. And you can do all the tricks that you want. So now I'm calling the binded function inline. So instead of doing, this is really bad, really bad. It's a cut and paste from the examples. So, okay. So let's see what happens here. So in the first case, I create a bind to foo, the placeholder 1 and 4, and I call it with argument 6. So this is just creating the binder and calling it in the same line. Okay, the second parenthesis is calling. And now it's like will be 6 plus 4. When I call this function, it will be 6 plus 4. The output will be 10. What about the second one? What do you think happens here in the foo underscore 1 underscore 1? Anyone? Is it the legal code? Does it work? Yep.
I would guess 6, 6 then?
Yeah, 6, 6. You take the first argument of the binded function, and you pass it to wherever underscore 1 happens. So you have like a sequence of argument, the first, the second, and the third. Whenever underscore 1 happens, you take the first argument. Whenever number 2 happens, you put the second argument, etc. Right? So this is 6 plus 6. If I do like this, number underscore 2, I take the second argument. So this will become 8 plus 8, 16. And of course, I need to pass 2 arguments there. The first will be completely ignored. But I need to pass it because I need to have access to the second argument in the argument list. And I can, for instance, swap position. So this will become, this binded 6, 4 will become foo of 4, 6. In this case, it doesn't matter. The operation is commutative. But in other cases, you might want to switch things around. So this look quite easy. The efficiency of the binder is good. Okay, so the compiler can do all. It's implemented with a lot of template tricks, and the compiler can inline everything. The things can really work efficiently. So calling the binder function and calling the original function has exactly the same cost. Usually, if it is inlined in the original one, it is inlined also in the binded. So efficiency is not the concern here. The concern here is how to, for instance, this binder can be used to adapt one function to some other library, a library that requires a certain function to work, and you have another function, and you can simply swap arguments here and there, or and do the operation that you want without changing the code, without writing new code, just writing a single line to bind. I don't have my watch. What time is it? 9:30? Okay. So there is a problem here, though, that suppose that that function requires not just integers as arguments, but references. This will go, this is not a reference, this is just an R value. And when you try to call a function that takes a reference, with this guy, it will give you a compiler error saying, well, this is not the reference, cannot have a reference on this guy. So you got in trouble when you have references. So of course they thought about this. So if I have a function bar that takes two references to integers instead of integers, and I can still bind one argument to a variable, but I have to use a special syntax which is stdref. So I take my value x as a second argument, and I embed it into stdref x. I'm saying I want the reference of this guy. I keep it number one. Number one doesn't need to be qualified anyway. It will know if it is a reference or not. How does it work? With the perfect forward that we saw a couple of yesterday, I don't know, some time ago. Yeah. So the perfect forward allows this guy to know, okay, whatever placeholder, whatever comes in, I will pass it to the function. I don't really care what it is. So this is an application of the standard forward again, which allows this syntax. Otherwise, you cannot have this syntax. You have to specify references on placeholders. It becomes extremely ugly. But this allows you a kind of limited complexity syntax. You only to specify the referenceness for the arguments, for the explicit argument, not for the placeholders. So this guy, if I call with y, it will call y as the first argument and x as the second argument. It will be 6 plus 4, but the second argument will be incremented, so after this call, x will be 5. So it will behave exactly as you would expect, right? You have a reference, so you're passing a reference to it. Questions? In the case in which you want to force a const reference, in this case it's not necessary, but sometimes there are cases in which you want to force a const reference, then you can use stdcref. And this becomes like a const reference to x. Now the syntax is easy, the implementation is very complicated, but the syntax is very easy. If you want to see like a code that has a very simple API, like cref or stdref, very simple interface, and you want to see how they implemented it, you go into standard library and look at the implementation, and it will take some time for you to understand what happens in there. They're really playing all the tricks, basically, to get this thing to work so easily, right? Easy for you, complex for the library developer. That is the philosophy. The library developer is the one that works hard to make life easier for the others. I'm a library developer. I'm a kind of Robin Hood, something like this. Yeah.
In which case would you use a stud bind instead of a lambda?
Sorry, I didn't get the question.
In which case would you use a stud bind instead of a lambda?
Well, in case, for instance, in which my function is given by somebody else, or some legacy code that has a function that I cannot change, or I don't want to change, then I can just use that to bind to a function, and then change the interface of that function and pass it around. If I can use a lambda, I should always use lambda.
I mean, you could also use a lambda to wrap that function, as you do with stud bind.
Seemingly, but if you have to bind arguments, then you have to do capturing. And so you have to initialize data members. So the construction of that thing might be more complicated. So you can do it. In some cases, this is actually, I think, is better. But yeah, basically, using a lambda will force you to do it explicitly, to write it, also with a captured list and everything. So I think in some cases, you really want to use the bind. But yeah, you're free to do it as you want. Kind of. It might be worth it to use lambda because lambda is convertible to a function pointer. So you might want to do that because you want to pass lambda to something that accepts a function pointer, and then it will become automatic. While with the binder, it will be difficult. That is a good point then. So if you really have to use function pointers, then you use lambda. And this comes in this next slide. This is slightly more code. And we saw a lambda is a function created on the fly, which is converted automatically. It has the conversion operator to the function pointer. STD function doesn't do it. If you pass an STD function to a function that accepts a function pointer, you get a compilation error. And same thing for the binder. The binder is a complex structure. It's a complex template class, and it cannot be converted easily to a function pointer. So lambda can do it because it's basically a language feature, and the other ones do not convert easily to function pointers. So let's see that if I have a function, a run, that takes a function pointer as the example we had before, and I pass a lambda to it, that's perfectly fine. Same example we saw before. And now I want to run std bind of foo. Well, in this case, it wouldn't really work because it would take a single argument. But it's not because it takes a single argument it doesn't work. It doesn't work because bind is not convertible to a function pointer. So this guy does not work. Also, if I have an std function, foo, my f, right, is my f equal to foo, and foo is this function here, and I call run on my function, that doesn't work either because std function is not automatically convertible to a function pointer. So to do that, when I have a standard function and an std function, I use the target member function, the target method. The target method just, you have to specify my function, which is my std function, my f, right? Target with the signature of the function pointer I want to have, the function pointer type that I want to get in the output. And I call it without arguments, and I get the pointer to a pointer out. So I need to dereference that pointer and pass it to the run function. The deal is that if I pass the wrong signature, so it's a signature not to the function that is actually being stored inside my function, I can check it by check that the pointer which is pointed to is null pointer. If it is a null pointer, then it means that the target method didn't succeed, and the function I cannot call. I mean, I can call that run function, but I get undefined behavior because the pointer is null. Does it make sense? This is the price you have to pay for having library features instead of language features. So in case of member functions, I can bind, I can do standard function, I can do the things with member functions. In the case of member functions, remember, if it is a static member function, like a member, it takes an integer and get an int, well, you just bind it with this syntax, with a : member, and this will become a function that takes two integer and return one integer. The fact that it is inside a class is like being inside a namespace. Not much of a difference. And then you can run the target method in your function, and then you call it, and you call this member function. On the other end, if I have an object and I want to bind it to a member function which is not a static, like member2, I should work on names, I guess. So I can bind a standard function to this member, but I can create a standard function to that member, but I have to remember that a member function takes n plus 1 argument, and the first argument is the pointer to the object that from which I'm calling this member function. So it is to bind to this guy, you have to pass a signature of the function takes a pointer to the object, the arguments, and returns whatever it has to return. And then you have to pass these syntax, so the address of a column member 2, and this is the syntax to refer to a member function of an object. Okay? And then I can call it, and when I call it, I have to pass the address of the object, so address of A, and the arguments. And then this is the example you have in your code, and it will show, we call 3 plus 4 will show you 7. I can use bind to pretend to have a function with 2 arguments instead of a function with 3 arguments. If I bind my first argument to the address of the object, and then I use the placeholders to refer to the arguments. And so now I can call member3, which is this function with 2 arguments only. But this will be translated into the member function member2, which is non-static member function, in which the first argument is this object, and the other ones are the one that I explicitly said there. Does it make sense? This is exposing something that we never want to see, which is how classes are actually implemented. Well, they are implemented in a very simple way. When you have a member function, is not stored in some magic inside the object, which contains the code of the guy, and it's just a regular function put somewhere in your object, in your executable file, and we'll have a signature which takes an extra argument that the compilers pass there, which is the pointer. And so you have to, in this case, you really have to know that. You have to know that that member function is called that way. So you can see what's happening inside. Best practices, just to conclude, are lambdas are good. Use lambdas when you can. It simplifies our code. They are efficient. They can be inline easily. Beware of the lifetime considerations when you capture references. But apart from that, it's a really good. Bind is as efficient as lambdas, or as efficient as just calling a function. So std bind is efficient. Std functions have a runtime overhead, so you should use them only when you really need. But they're very powerful. They really are powerful. So in many cases, you want to use standard functions simply because that's of your runtime constraints. If you have to use them, you use them, and it works. And there are a few fixes, actually, in the standard function behaviors coming in. And that concludes this presentation. Yeah. Questions? Okay. What should we do? We can either anticipate coffee break or do one pattern. Maybe we can do the CRTP pattern. Okay.